Good afternoon, everybody, and welcome to our penultimate Geo lecture of 2020. This afternoon, we're joined by Sylvia Knight. Sylvia is the Head of Education at the Royal Meteorological Society. In her position, she supports the teaching of weather and climate across the UK in schools and education centres. And today, she'll be presenting to us the weather of 2020, so looking at the global processes that determine weather in the UK and how COVID-19 has actually had an impact on weather and climate around the world. Now, as usual, keep an eye on the chat and don't forget to leave any questions and comments you have throughout the session. And there will also be a few links and bits and bobs popping up through the session to share with you about the presentation. Okay, so when you're ready, Sylvia, over to you.
Thank you. Right, so yes, this year's weather, it's been strange, hasn't it? Like everything else about this year. It felt like we had summer weather in the spring and then we had autumn weather in the summer, and that sort of carried on into autumn. And you can understand why that is and what's been going on. And through that kind of, it's a nice way of looking at the kind of global processes which determine what weather we get. So I'm going to start off by asking you what your favourite weather is. And I think there's a this SurveyMonkey link's going to appear magically in the chat now, I think. And if you want to follow that link, I'd like you to tell me what your favourite weather is. Is it a thunderstorm? Is it snow? Is it one of those clear, frosty, beautiful winter mornings? Is it autumn sunshine? Is it summer sunshine when it's really hot? Or is it a really good storm with gales and wind and rain? Or is it something completely different? So if you'd like to go to that chat now, I'd like you to vote for that. And at the end of the talk, I'll show you what everybody put. So if we consider what the weather did this year and the records that have been broken, it was the wettest February on record for England, Wales and Northern Ireland and the UK as a whole. And it was the second wettest in Scotland. After that, it was the sunniest spring since 1929, the 8th warmest and the 5th driest for the whole UK. May was the driest on record for England, the second driest on record for Wales. June, July and August, however, saw some places getting over double their average rainfall totals. And in June, a place in Scotland, Tullochbridge in Inverness, measured a minimum temperature of minus 1.9 degrees in June. On the other hand, we had some very warm spells in the summer too, and the maximum temperature was 37.8 degrees at Heathrow near London on the 31st of July. Armagh in Northern Ireland had the wettest August for 12 years and the dullest August for 33 years. And more recently in October, we had the wettest day ever in UK records. So it's definitely been a fairly unusual year with all sorts of bizarre weather going on. And then if we look at storms and the storms that have been given names, so a storm is named if it's predicted to have a significant impact on us, whether that's through its wind or through its rainfall. And the storm season we would normally expect to start in the autumn and run through to the spring. Over the last winter, the first storm was named in December. That's a fairly late start to our winter storms. We just had the one storm in December, then Brendan in January. Then we had 3 in February, which brought us all that rainfall. That was Kira, Dennis and George. And that was the end of our winter storm season. And then we had 2 more storms, named storms in August, Ellen and Francis. That was the first time that storms had been named in August. We started naming storms in 2015. So it was really unusual to have 2 significant weather events in August. So it really was a pretty weird year. So to summarise all of that, February was stormy, but then after that, the spring was sunny and dry for most people. Summer was a bit disappointed. We had storms in August, but there were hot spells too. And we're going to look at these weather events, these things in turn, and see why we had this unusual weather. And if we just take a step back from that, I don't know whether you saw in the news yesterday, the World Meteorological Organization announced that 2020 was set to be one of the 3 warmest years on record. This, and I think the last 6 years, so the 6 years from 2015 to now, are the 6 warmest years on record. So looking at the globe as a whole, this year has been abnormally warm. This temperature map shows the temperature anomalies for the whole year, and you can see that most places in the world are pink or red, so most places were warmer than you'd expect. With an exception here in the South Pacific, it was colder, and that was the start of a La Nina event that's still developing. I'll speak a bit more about that later. And normally during a La Nina year, we'd expect the whole Earth to be slightly cooler than normal. So for most of the rest of the world to still be warmer than normal in a La Nina year is extremely unusual. And the really big thing that strikes you in this map is this huge patch of very, very warm temperatures in the Russian Arctic, which led to all kinds of problems, particularly near the beginning of the year. So next, we're going to take a step back again and remember the difference between weather and climate. And I'd like you, because I can't stream that video here, I'd like you to follow the YouTube link and to look at the short animation, which just illustrates in a really nice way, I really like this, the difference between weather and climate. So hopefully you're seeing the link to that now, and I'll just give you a minute or so to go and look at that. Right, hopefully we've got everybody back. Yeah, I really like that animation. I think it shows really clearly how the weather can be very different from year to year, but still there's a climate which is the average of all the weather. And that could be summarized quite neatly as weather is what you get, climate is what you expect. So if we think about what weather we expect, we generally expect the summer to be nice and warm and for there to be few storms. And then we expect a stormier, a wetter, a windier autumn and winter. I think the only exception to that is maybe in the far north of Scotland, where they can still get storms. The climate would still lead them to expect storms in the summer, but they'd expect those storms to be less damaging, for there to be less wind and less rainfall associated with them than the storms that they get in the winter and autumn. So let's think about why we have a climate and what determines what weather we expect. Ultimately, it's because we get our energy from the sun. And the sun is a very hot star, and so most of what it gives us is light and heat, and also ultraviolet radiation. So that's the energy we get from the sun, and it shines on the Earth's surface. And because there are, through the year, bits of the Earth's surface which are pointing directly at the sun, in those places, the sun's light is focused in a fairly small area, and there are other places which are further sloping away from the sun, where the sun's light is more spread out, and so the sun's energy is spread over a larger area. And so those places end up being colder, just because the sun's energy is more spread out, so they don't get warmed up as much by the sunlight. And there are places where the sun is overhead, where the ground gets warmer just because the sun's light is more concentrated. And so, unsurprisingly, if you look at a temperature map, you see the places in the tropics where the sun is overhead, high in the sky, the temperatures are warmer, and then the temperature falls off as you go towards the poles. And you can look at that in other places too. If you've never been to the earth.nullschool website, do, not now, but at some other time. It's a lovely way of looking at current conditions on the surface of the Earth, so both in the atmosphere and on the land and in the oceans. And so this is a snapshot from a few days ago showing the temperatures on the surface of the Earth. And again, you can see these warmer temperatures in the tropics and the colder temperatures at the poles. And over the course of the year, as the place where the sun is overhead changes, you'd expect the warmest temperatures to shift up towards the Tropic of Cancer, and then down towards the Tropic of Capricorn through the year. So there are going to be places on the Earth's surface where the land surface is warmer, and other places where the land surface is colder. And where the Earth's surface is warmer, you'd expect that to warm up the heat, to heat up the air above the ground. So what happens to that air as it gets warmed? Well, I've got a little experiment to show you. This experiment requires a tea bag, the sort that comes with a tag attached, which you can take off and open up the tea bag and pour out the tea. What you're left with is, once you open it up, a cylinder of tissue paper, which I am going to stand up on a tile. Actually, I might just move my camera down a bit so that you can see that. That's good. So I've got a cylinder of tissue paper on the tile, which I'm going to set fire to. It's on a tile just in case I don't want to set fire to my desk. It's actually very unlikely to, but just in case. Right, so I'm going to set fire to that. Right, so the tea bag's burning. The warm air that is rising up off the top of the tea bag, and as it burns down, the tea bag's getting lighter until, oops, sorry, I missed showing you that, but you should have seen that the tea bag suddenly took off and rose up through my rim. So warm air rises. Everyone knows that, but it's a really nice demonstration of it. So if we've got places on the Earth's surface where the warm Earth is warming up the air above the Earth's surface, you'd expect that air to rise. And so you'd expect there to be places on the Earth's surface where warm air is rising in the tropics. And conversely, in the polar regions where the ground is coldest, you'd expect the cold air there to sink. So if that was the only thing that was going on, you'd expect there to be warm air rising in the tropics and cold air sinking in the polar regions and circulating in both hemispheres like this in a very simple little circulation. But it's not that simple. And it's not that simple because we live on a rotating planet. And if you think about it, over the course of a day, if you're standing on the equator, you're moving a colossal distance through space, 2 pi times the radius of the Earth, which is 6,370 odd kilometers. You're moving really fast, but the air around you is moving at the same speed, so there's no wind or anything to tell you how fast you're moving, so you don't notice it. On the other hand, if you're at the poles, over a course of a day, the Earth is spinning, you're just standing on the spot and turning around on the spot. So the air around you, similarly, isn't moving at any speed at all. Now, what happens if really slow-moving air from the poles is being drawn down towards the tropics to replace that rising air at the tropics? Well, you should be able to see that that air gets left behind as the Earth rotates around it, and it looks like it's becoming ever more easterly. If I move that down, I'll show it to you again. So slow-moving air from the tropics gets drawn down towards the poles. The Earth moves underneath it because the Earth is then moving faster than the slow air that's coming down from the poles, and so the air looks like it's becoming ever more easterly. And that's a Coriolis effect. And there are lots of other ways of demonstrating it. This is quite a nice one. So I've got a sheet of Perspex pinned to this atlas and a Sharpie there. So what I'm going to do is I'm going to draw a straight line in that direction with my Sharpie, but while that's happening, I'm going to rotate the Perspex underneath. So if I just rotate that and draw, so I've drawn a straight line, but what I've ended up with on the Perspex, oh, that doesn't show up at all, does it? Here we go. Hopefully you can see that what I've ended up with is a curve. And that curve looks like it's going from the middle, and then it kind of is going around clockwise if you look at it like that. But if I turn it round and look at it from the other side, the curve goes in the other way and looks like it's anti-clockwise. And that's the key, really, to why storms rotate in opposite directions and the two different, the air or anything gets deflected in the opposite direction in the two different hemispheres. It's simply because you're looking at it from the other side. So just like you looked at that Perspex from on top and then underneath, and it looked like the curve was going around in the opposite direction, that's a simple reason why air gets deflected by the Coriolis effect in different directions in the two hemispheres. So to summarize the Coriolis effect, explaining it is more complicated. I had to go, if at some other point you want to follow that YouTube link, you'll see my attempt at fully explaining what the Coriolis effect is and how it works. But the simple summary of it is that in the northern hemisphere, the rotation of the Earth means that all moving objects are pulled to the right. So if they're going north, they get pulled to the right and become more westerly. If they're going south, they're pulled to the right and they become more easterly. Similarly, anything going up or down or whatever direction it's going in, it always gets pulled to the right by the Coriolis effect in the northern hemisphere. In the southern hemisphere, it gets pulled to the left. So that means that instead of our nice simple circulation with the air rising up in the tropics and sinking in the polar regions, we have our air rising in the tropics at the intertropical convergence zone. So that's the bit of the Earth's surface which is warmer, which meanders from the Tropic of Cancer in our midsummer to the Tropic of Capricorn at about this time of year, a few weeks' time. And the air's rising there. It goes off towards the poles, it gets deflected to the right by the Coriolis effect, becomes ever more westerly till it is just a westerly and the whole circulation collapses and it sinks down back to the ground. It then returns back to the tropics. This time it becomes deflected to the right again and it becomes an easterly and gives the trade winds. So that's the Hadley cell. We've got something similar going on in the polar regions, the polar cell, so driven by the cold air sinking. And then in between, you've got the Ferrel cell, which makes no sense at all because it looks like you've got warmer air sinking there and colder air rising there. But in fact, the Ferrel cell is just driven by the Hadley cells and the polar cell by that air, dragging the air along with it. And also, if before I say carry on, I'll just show you. So the polar cell, it's got very cold air trapped inside it. So we have relatively cold polar air in the polar cell, whereas the air is much warmer in the other cells. And so we call this the polar front, where the Ferrel cell meets the polar cell, where cold air is meeting warmer air. And that's really critical to the weather that we get in the UK. But again, this is from Null School a couple of days ago, showing the winds on the surface of the Earth a couple of days ago. And you can just about make out the easterlies all around the tropics, the surface easterlies that are associated with the Hadley cell, with a bit of imagination, you can make out the easterlies in the polar regions from the polar cell. The polar cell is much weaker than the Hadley cell, but there's nothing that looks like the feral cell in mid-latitudes where we are. There's just this mess of swirling storms. And that's really what the feral cell is like. The feral cell is the average of all these complicated air motions due to the depressions that we get in the mid-latitudes. But the crucial thing is that they're carried on westerlies because of the feral cell. And so all these depressions tend to come at us from the west. So we have this polar front where cold air meets warm air. And that brings us weather because of stability. So you know that if you have a ball on a hill, if something nudges that ball a little bit, it ends up a long way away from where it started. That's a very unstable situation. On the other hand, if you have a ball in a valley and that gets nudged, it ends up back where it started. That's a very stable situation. Turns out that the polar front is unstable, and so the westerly winds blowing along it, if something nudges them, it grows very rapidly as a wave. So if we've got our westerlies blowing along the polar front with cold air to the north of it and the warm air to the south of it. If something nudges those westerlies, for example, if you've got a mountain here or something like that, then that westerly will kind of bulge around the mountain, and as soon as the mountain's out of the way, because it's unstable, the nudge grows as a wave, just like an ocean wave approaching the seashore grows. In exactly the same way this atmospheric wave grows, and in just the same way that an ocean wave at some point gets so big that it can't hold itself together anymore and the wave breaks, in exactly the same way this atmospheric wave gets so big that it breaks. And when that happens, the wave breaks, and what we're left with is warm tropical air on the poleward side of the polar front and cold polar air on the tropical side. So I've got an animation here I think you can see, which shows a week's worth of airflow, and you can see the warmer temperatures here from the warmer air in the feral cell, and here you've got the colder polar air to the north of the polar front, and the polar front's where the blues meet the greens, and you can see that there's wave after wave developing on the polar front because it's so unstable. I think we're about to come to the end of the animation, but we just wait. So here's one that's growing, it's growing, then it begins to break, and you end up with the warmer air stranded on the poleward side of the polar front. This is going on all the time. This continuously throughout the year, weather systems developing on the polar front. So why do we get weather associated with all of this? Well, if we've got warm air rising, if we've got warm air meeting cold air at the polar front, it's always going to be the warm air that rises. So what happens to it? Well, I've got another little demonstration to show. So here I have a bottle with some liquid in it, which you might just be able to see. And first of all, I'm going to increase the pressure in the bottle using a bike pump, which I'm just going to stick in the top of the bottle. Right, so I'm going to use the bike pump to firstly increase the air pressure in the bottle. So at the moment the bottle's quite squidgy. I'm going to increase the air pressure in the bottle. And pressure's related to temperature. So as the pressure increases, it's going to get warmer in there. And that should hopefully encourage a bit of evaporation of that liquid in the bottom of the bottle. So that bottle is now really quite firm. There's lots of extra pressure in there. I'm going to let it out very suddenly. So the pressure will fall very suddenly, the temperature will fall very suddenly, and hopefully we'll see what happens. You should see that we've got a cloud that's formed in the bottle. I'll do it one more time there because I'm not entirely sure whether my connection dropped out for a bit. So I'll just do it once more. So you can see there's still a bit of a cloud there. The pressure's low at the moment. I'm going to increase the pressure, and you should see the cloud vanishes immediately as the air warms up, as the pressure warms up, as the pressure increases. So we've got high pressure now, a little bit more. Let the pressure out very suddenly, and you should see the cloud form. Right. I like doing that one. Okay, so wherever we've got warm air meeting cold air at the polar front, sorry, there we go. Wherever we've got warm air meeting cold air at the polar front, the warm air is going to rise. As it rises up through the atmosphere, the air pressure falls, and so it cools. And as we've just seen, as the air cools, at some point, the rate of evaporation becomes less than the rate of condensation. And that's when we're going to get cloud droplets forming. And once you've got cloud droplets forming, at some point, they're going to get big enough to fall as rain. So we've got warmer air and cold air meeting. We're going to get clouds forming. We're going to get rainfall. And that releases latent heat into the atmosphere, which is the energy source for the whole developing system. And all the cloud and rain that's formed is caused by the warm air rising in this case. So what does that mean in terms of the weather? Well, here we've got the polar front here, cold polar air to the north of it, warm, more tropical air to the south of it. Something's nudged the polar front. We've got westerlies blowing along it. So here we've got westerlies coming in behind the cold front, which is drawn here in blue, and pushing into the warm air ahead of it in the centre. And that means we've got warm air meeting cold air here on the cold front, whereas on the warm front, which is drawn in red with the little semicircles on it, there we've got warm tropical air from the centre pushing into the cold air ahead of it. And then as the wave develops, that whole kink develops too, and the whole pressure fronts develop as well. If we look at that in 3 dimensions to see what's actually going on, so we've got that same situation with our nice depression beginning to develop on the polar front. If we take a cross section through that, so through from the cold air behind the cold front, through the warm air in the middle, through the warm front, and out to the warm air, the cold air ahead of the warm front, and draw now height against distance through that, and draw those fronts on. The first thing to see, of course, is that the fronts aren't vertical; they slope, and they have to slope because at the cold front you've got cold air pushing into the warm air ahead of it. And because it's the warm air that's got to rise, the cold air goes in underneath it. So it's sort of bulldozing its way in underneath the warm air ahead. Whereas at the warm front, you've got warm air pushing into cold air ahead. It's the warm air that's got to rise. So it rises up and over the cold air ahead of it. So the whole thing's moving from west to east on those westerlies associated with the ferrule cell. You've got the warm air in the middle. You've got warm air rising up both the fronts. And therefore that's where you get the cloud, that's where you're going to get the rainfall. Fronts are drawn on a weather map at the place where the front meets the ground. And it's also interesting to note that actually the slope on those fronts is really, really gradual. It might be on the warm front, it might be 1 in 150, which means that for each 150 kilometres you go across the Earth's surface, the front has only risen by 1 kilometre. So these are really, really massive features. I was going to show you this little animation of the passage of a depression and the weather that you experience as a depression passes over at this point. But I think rather than send you away to look at that, maybe you can just make a note of that YouTube link and watch it in your own time. So we'll just skip over that one. And instead, we'll think about why these things are low pressure systems. So when we talk about atmospheric pressure, you're simply referring to the pressure, so that the weight of the air above you that's pushing down onto the Earth's surface. So if atmospheric pressure is high, it means there's a lot of air above your head. If atmospheric pressure is low, there's less air above your head. So if you think what's happening in the centre of depression, on both those fronts, you've got warm air rising. If the warm air is rising up through the atmosphere, it rises up until it hits the top of the troposphere. So the troposphere is the bottom 10 kilometers or so of the atmosphere, which has all of our weather in it. The air can't cross into the stratosphere above, so it spreads out sideways along the top of the troposphere. Similarly, the rising air's got to be replaced at the surface, so the air's coming in at the surface to replace that rising air. But that air that's coming in at the surface is being slowed down by friction. So it's a lot less easy for that rising air to be replaced at the surface than it is for it to spread out higher up. And so what that means is that you end up with more air spreading out at the top than is coming in at the bottom. And so we end up with less air in our column because it's not being replaced as quickly as it's being removed. And that's where the air pressure falls, because you quite literally have less air there as a result. So you end up with some places in the atmosphere which have less air, low pressure, and other places in the atmosphere which have more air, that's high pressure. And that's exactly the same as if you have two buckets of water like here, one with more water in it and one with less. Now, you know intuitively that if you take the barrier away between those two buckets, the water will flow very rapidly to equal out the pressure, to balance the water level in those two buckets. And exactly the same wants to happen in the atmosphere. The air wants to flow from where the pressure is high to where the pressure is low to equalize the pressure. But unfortunately, we're on a rotating planet, and so that can't happen. The Coriolis effect gets in the way. But before I say that, it's the pressure difference. So we've got air that wants to flow from high to low, just like the water did. And it's the bigger the pressure difference, the bigger the difference between the high pressure and the low pressure, the faster the wind's going to move. And so if you think about the pressure contours on a weather map, they mark how quickly the air pressure is changing across the surface of the Earth. The closer those pressure contours are to each other, the isobars, the faster the wind's going to blow. So the closer the pressure contours are to each other, the windier it's going to be. But we live on a rotating spherical planet, and the Coriolis effect means that the wind doesn't actually just blow from high to low. It actually ends up blowing around our pressure systems in an anti-clockwise direction in the northern hemisphere, around a low pressure system. And so yes, we end up with anti-clockwise winds blowing around low pressure weather systems and clockwise winds blowing around high pressure systems, because it's only with circular motion that you can get a balance between the Coriolis force that's pulling everything to the right and the pressure gradient that's pulling everything from high to low. Circular motion around the system's the only way that those two things can be in balance. So now we need to think about the jet stream and what this is. So the jet stream is a belt of very fast moving air with wind speeds up to about 200 miles an hour, high up in the atmosphere at about 10 kilometers. So again, at the top of the troposphere. It's about the same height which aeroplanes fly at. And you can see here that the jet stream goes from North America towards Europe. It's a westerly again. And so if you're in an aeroplane wanting to get from North America to Europe, you want to be in the jet stream because it's going to get you there faster. If you're going the other way, you want to be as far away from the jet stream as you can be because it's going to slow you down. Now, the jet stream effectively marks the position of the polar front. The jet stream 10 kilometers up is where that polar front is on the ground, which is also where we've said that those storms, those depressions, those low pressure weather systems are forming. So the jet stream is a really useful marker of where a depression is going to form and the path it's going to take after it forms. But if you plot all the positions of the storms in a year and you plot where the jet stream was, they'll be in the same place. So it's a really, really useful marker. And the polar front and the jet stream and those storms are all linked with each other. So normally in the winter, we'd expect the jet stream, so that's this lower diagram here. I'm not sure whether you can actually see my cursor. Normally in the winter, the jet stream, the polar front, the jet stream, and therefore all those depressions track pretty much across the south of the UK. And that's why we expect to get storms in the winter, because it's all south of us. Now, as a whole pattern moves northwards in the winter, in the summer, as the intertropical convergence zone moves north, as the sun goes overhead over to the Tropic of Cancer, the whole pattern of the whole global atmospheric circulation moves north. And therefore, normally in the summer, we expect the polar front and therefore the jet stream and therefore all those storms to track further north. They might still be over the very far north of Scotland, so they might still expect to see a few storms. But on the whole, the south of the UK gets much better weather in the summer, normally. If we look what actually happened this year, this chart on the right is from the 24th of July. So the summer, when we'd normally expect the jet stream, the polar front, all those storms to be further north. This map shows the jet stream, so upper level wind speeds. And you can see here that the jet stream is very much south still. And that was why in late July, early August, through August, we were still getting the stormy weather that we wouldn't normally expect to get in the south of the UK in the summer. If we look at some other jet stream maps, the one on the left shows December to February. That's a very normal looking jet stream chart. The colours show the intensity of the wind, and you can see again it's over the south of the UK. That's where you'd expect it to be in the winter. And then the one on the right shows March to May. And you should just be able to see from the wind arrows that the jet stream was coming across the North Atlantic towards us, and then it buckled up over and above us. And of course, that's where the polar front was, and that's therefore where all the depressions went up and over to the north of the UK. And that's why we had that lovely weather in the first lockdown, why we had clear skies and we didn't have any storms, and the weather was so much better than it's been in the second lockdown. And related to that, we need to think about high pressure weather systems. So high pressure simply means that there's more atmosphere above your head, and that happens when the air is sinking. If the air is sinking, then it's coming in high up in the atmosphere faster than it's able to flow out at the ground because of friction again. And so the amount of air above the ground accumulates, and we end up with higher pressure. If the air is sinking, then as it comes down through the atmosphere, the atmospheric pressure will increase. And as the pressure increases, the temperature increases. And so you get lots of evaporation, like in my bottle when I first started pumping air in. And so we tend to get clear skies when there's high pressure. And you can see on these charts here that where there's high pressure marked over the Bay of Biscay, the corresponding satellite image shows a clear sky over that area. So an anticyclone is a high pressure system. We tend to have circular clockwise winds blowing around it. We associate them with sinking air because as the air is sinking, the air accumulates, and so the surface pressure rises. They tend to be larger than low pressure systems. They tend to last longer than low pressure systems, and they tend to have very light winds blowing around them. And on the whole, because the sky is clear in the summer, that means that the sun's light can get down to the surface and warm us up and give us glorious warm summer days. If we have high pressure in the winter, it means that the ground, if the skies are clear, there's no cloud or anything to insulate the ground, so it can cool down a lot overnight. And that's when we wake up to those beautiful, sparkly, cold winter mornings, frosty mornings. So mostly when we have anticyclones, we expect the weather to be quite nice, but not always. In the late winter and the early spring, if the ground cools down so much overnight that it cools the air immediately above it down to the point where cloud droplets can form, then we can get fog or very light, very low cloud forming. And if that forms overnight, then because there's very light winds associating with our high pressure, there's no wind to blow that cloud away. And if it's winter, then the sun isn't warm enough to evaporate that cloud in the day, so it just tends to stay put. And that's when we end up with anticyclonic gloom. It's just grey and gloomy, sometimes for days on end. Probably not raining, so it's not heavy enough cloud to give us any sort of precipitation, but it just stays put, and we don't get any sunshine at all. So high pressure doesn't always mean good weather. But if we look at some charts for this year, so this chart is for the 15th of April, so right in the middle of the first lockdown. So that was when the polar front was to the north of us. That's where the jet stream was, and therefore that's where all the storms went. And you can see these curling fronts indicative of those storms all going off to the north of us. And we've got high pressure over the UK. And that was why we had such nice weather in the first lockdown. So that's the 15th of April. This chart's from the 15th of May. We've still got that high pressure. The polar front has moved down a little bit. So we've got some storms maybe beginning to affect the north of Scotland now. But for the most of the UK, high pressure still dominated. And we see that when we look in rainfall charts. So these are chloropleth maps of the rainfall that we had in April on the left and in May on the right. And the white or brown colours indicate less rainfall than we'd expect, so less than the climate. And you can see that certainly in April, all the UK was very dry. In May, as I said, that north of Scotland beginning to get a bit more rainfall than they'd expect in the climate. But for the south of Wales, the southwest and the southeast and the Midlands of England, there was very much less rainfall than the climate would suggest. And for most of the rest of England and Northern Ireland and southern Scotland, it was a bit less than they'd expect. So it was a very dry April and May. And in fact, we had record-breaking pressure on the 29th of March. A pressure value of 1,055 millibars, hectopascals, was recorded, which was the second highest only after December 1926. So it really was very much dominated by high pressure in that time. Take a step back and look at the global pressure patterns. Again, this is an image from Null School. So thinking about those three circulation cells, we'd expect there to be low pressure where the air is rising over the intertropical convergence zone. We'd expect there then to be high pressure where the air is sinking at the edge of the Hadley cell, the poleward edge of the Hadley cell. Then low pressure where the air's rising at the polar front, and then high pressure again in the poles where the air is sinking. And you can see that in this image from Null School. You can see the lower pressure values here around the equator, then these areas of high pressure at the poleward edge of the Hadley circulation, and the high pressure again at the poles, and the kind of low pressure around the polar front here. And it's these semi-permanent areas of high pressure. So this one's the Azores High and the Siberian High, and then the high pressure area over the North Pole, that have a big impact on our weather as well, because if that air is coming from there, it has certain characteristics. And that's where people talk about air masses. So if air is coming up from the tropics, from that Azores High, that's called tropical maritime air, and there are the other air mass names which you've probably heard of. The diagram on the right shows you our the wind directions that we get. It's a windrows showing where our wind comes from most often, and you can see that most frequently our wind direction is westerly or southwesterly, and that's associated with polar maritime air or tropical maritime air that's coming in from the west. So that would be either the polar air from the north of the polar front, or the tropical maritime air from just to the south of the polar front. And so depending where we are relative to the polar front, we get one of those two air masses most of the time. On the 10th of May, we had something a bit different happen. So the 10th of May was the day that Boris Johnson announced how we were going to come out of the first lockdown. So it was quite a memorable day. And weather-wise, it was quite interesting too. So again, on this snapshot from Null School, you can see the wind arrows just coming down the North Sea, showing us northerly winds. And in fact, that air, you can follow it all the way up to the Arctic. So that was air that was coming straight down at us from the Arctic maritime air. And it came down as with the polar fronts, the whole thing just suddenly moved towards the south. You can see the polar front marked on this weather chart. There was high pressure to the northwest of us, and then the air blowing around that in a clockwise direction was what brought us those northerly winds. And that polar front just came down suddenly across the UK over the course of the 10th of May. And you can see that quite nicely. These are temperature measurements from the centre of Manchester. And you can see that's a week. You can see that normally the temperature rises in the day and then sinks and then rises and sinks. But then on the 10th of May, it never rises in the middle of the day. So that polar front passed over Manchester early morning. And after that, the temperatures just sank through the day as that Arctic maritime air dropped down over the UK. So it looks on this chart like the polar front arrived with the Arctic maritime air behind it, sort of early morning. If we look instead at a similar image from the University of Reading, you want to be looking at the black line, which shows the air temperature. Again, on the so just get my so this is just for one day's temperature. So you can see the temperatures beginning to rise in the morning of the Sunday the 10th. But then again, you can see that polar front arriving at about 10 o'clock in the morning, and then suddenly the temperatures just fall. So I think it's quite nice to see how it arrived later in Reading, which is further south from Manchester, as the polar front and the Arctic air just moves slowly southwards down across the UK. Okay, so something a bit different to think about now. How did COVID affect the weather and climate? Maybe some of the things that a little bit less expected. So first of all, the impact of COVID on weather forecasts. We get weather measurements from all sorts of sources. We get them from weather stations and weather buoys, but those couldn't be maintained during lockdown. So as their batteries failed or whatever, we started getting fewer weather measurements from those. Radar, satellites, similarly, so there were some issues with the ability of people to maintain those. But the really critical thing that changed was the number of measurements that we get from aircraft. So normally on a day, you'd get about 50,400 weather measurements that have been recorded on an aeroplane from around the world. So that was 50,400 that we had on March the 3rd. That fell to under 10,000 by April the 2nd because of all the reduced flights. Now that weather data goes into the massive computer models that we use to forecast the weather. So there's an estimation that there was a 10% reduction in the quality of the weather forecast as a result of lockdown. Pollution, this is something we heard a lot more about. So air pollution is caused by things like diesel vehicles, by some industries releasing pollutants into the atmosphere, which reduce the quality of the air. So air quality on the whole did improve a lot as we all went into lockdown. So for example, in Wuhan, where the epidemic started, they saw a 93% reduction in some of the air pollutants during the lockdown period. But mostly these air pollutants are very short-lived. So as soon as people started coming out of lockdown, the air quality went back to its normal levels. In India, people saw the Himalayas for the first time in decades from places where the air quality is just normally so poor that they can't be seen. And we did see some improvement in air quality in Europe and in North America too. A more interesting link to pollution is the fact that there seems to be some evidence that people living in places where the air quality is normally worse tended to see higher death rates because of the COVID virus. That's because of the underlying health conditions that you see there. So certainly in North Italy, in those very industrial areas, there's some evidence that death rates were higher because of that. Another interesting kind of link between the virus and pollution is that places like Birmingham and Oxford and Leeds had plans to reduce city centre traffic and improve city centre air quality. And now because of all the other effects of the virus on our lives, they want to delay those plans. So in fact, air quality might carry on being worse as a result of the virus. What about the impact of the virus on clouds? So in general, when it's more polluted, there are clouds because cloud droplets need something to form onto. That might be pollen, it might be salt, it might be soot from natural fires or man-made fires, and it can be pollution. So in general, when it's more polluted, there are more clouds. So there's a period in the 80s and early 90s when there was something called global dimming because the air quality over Northern Europe was quite poor, and it was cloudier as a result, and that reflected the sun's light, and it was actually less bright on the Earth's surface as a result of that. And there are other examples of that. So people claim that maybe it rained more in Manchester during the week in the during the Industrial Revolution because of all the pollutants that the factories were emitting into the atmosphere. So did it get less cloudy during lockdown? Well, actually, for us, the fact that we had high pressure during lockdown meant that the pollutants that were there stayed put. I live in Greater Manchester. I looked down over Manchester and I could see the smog layer still over the centre of Manchester. It didn't move for those first few weeks of lockdown just because the air pressure was high. There was very little wind. There was nothing to blow the pollutants out of the way. So on the whole, maybe we didn't see the same improvement in air quality and the same possible reduction in cloudiness as a result. But the groundings of all the flights caused by the coronaviruses are giving scientists a really unusual, unexpected chance to study the impacts of aviation or on the climate system. What about other impacts? So we don't just pollute through the sort of pollutants that give us poor air quality. There's also greenhouse gases, obviously. And again, because of all the lockdown and the reduction in industry, there was a slight reduction in the amount of greenhouse gas, particularly carbon dioxide, that we're emitting into the atmosphere. But it really was only a very small reduction. China's CO2 emissions fell by about 25% over a 4-week period, but then they rebounded very rapidly to their normal levels. So this graph shows the annual cycle in the amount of carbon dioxide in the atmosphere. Normally you expect carbon dioxide values to go up in the winter as trees shed their leaves and those leaves decompose and release their carbon into the atmosphere. And then the carbon dioxide values fall in the spring and summer when the trees and other vegetation is forming new material and taking the carbon out of the atmosphere. And over and above that, you can see the slow, gradual increase over time as we're adding more and more carbon dioxide to the atmosphere through our through the burning of fossil fuels and through agriculture and land use changes. So the amount of carbon dioxide in the atmosphere this year was still higher than it had ever been before. It was ever so slightly lower than it would have been had there not been a coronavirus epidemic, but it was still much, much higher, well, significantly higher than it had been even last year. So what about the future? Well, I think coronavirus has given us a really unique opportunity to build back greener. There are the opportunity for various industries and things which have really struggled over the past year. We must make sure that only those industries which are going to help us to meet our aims in terms of meeting greenhouse gas emission reduction targets are supported, and that it's not the really polluting industries that are actively helped to recover after this year. And that's the real challenge, I think, to our government and others as we begin to come out and begin to recover over the next year or so. So to summarise, February was stormy. It was just an extreme version of normal for February. The spring was sunny and dry for most people because we had high pressure, because the polar front and the jet stream and all the depressions went to the north of us. Summer was a bit disappointing because the polar front didn't move north. It was still to the south, over us, and so we still had those storms unusually in August, but there was nice weather in between too. And then the climate's changing and we've got a real opportunity to do something about it. Now, what about the rest of the year? Well, as I mentioned very briefly at the beginning, there's a La Nina event building in the South Pacific. So then the South Pacific is colder than it normally is, and that has an impact on weather all around the globe. And for us, it can mean a mild, wet and windy early winter. That's what we'd normally expect. So the Met Office's 3-month outlook suggests that as a whole, we expect temperatures might be slightly more than average over the 3 months from November to January. But there's only a very small chance of that. There's not a great deal of certainty in that forecast. So as I wrap up and find out what you all voted for in terms of what your favourite weather was, I'm going to ask you another what was your favourite question, and hopefully you can now see a new SurveyMonkey link. I'd like to know what of all the things that I've shown you today was your favourite. Did you like the teabag rocket best, the cloud in a bottle, the difference between weather and climate animation? Okay, you haven't had a chance to see the passage of a depression animation, or was it the Coriolis effect demonstration with the Perspex sheet? So hopefully you can see another SurveyMonkey link there, and I shall see whether I can find the results of the earlier vote. So if you just bear with me for a minute.
Just jump in and join you for the last few minutes, Sylvia. That was really lovely. It provided so many different bits of information about how to look at the weather, and also some fun experiments to do as well.
So the results of the first vote was fairly close tie between snow, frosty and clear skies, and autumn sunshine. So there you go. Are there any questions?
Yes, if anybody's got any questions, please feel free to put them in the chat box. I imagine a lot of people are sitting trying to think about which experiment their favourite was at the moment. It was really interesting you mentioning about how the smog didn't go away in Birmingham, because I think when we all saw these images of the Himalayas reappearing in India, we thought, oh, well, you know, pollution's gone, that it would be a lot quicker than that.
Yeah, and it really wasn't here. Yeah.
I know, it's a strange thing. So I think it was fairly similar in Sheffield, actually. It took a little while for it to settle down and, you know, look a bit more like normal. But it's the same kind of thing. You can notice that the quality of the sky, the closer you get towards the city, does change. It's almost slightly grayer, which is a bit strange. Yeah.
Have there been any questions?
There don't appear to be any questions at current, but I'm sure that if anybody does want to provide you with any questions, they'll be able to get in touch with you at some point. I mean, I actually had a question of my own, which was to do with the planes. So you mentioned how there have been less planes gathering data, and also later on how it's the drop in pollution has allowed people to estimate how much planes do actually contribute to the problem. Do you think that as people realize that planes contribute to pollution, you know, there's going to be less up there anyway to record what's happening with the weather?
Yeah, that's an interesting question. I think nobody really knows how we're going to recover from this year, do they? There are a lot of airlines really struggling and really reducing their capacity. Are people going to start flying as much as they used to? It'll be really interesting to see. Who knows? If we stop getting so much data from aircraft, I'm sure that other ways will be innovated to get the same amount of data. I mean, we can get a lot of information from satellites, but not the same sort of information that we can get from aircraft. So, yeah, watch this space.
Yeah, because of course with aircraft you can get information about particle density and that kind of thing that you get at the higher atmospheres, can't you?
And you can also get the profile from all the different levels, which you can't, which is harder to do with satellites. Yeah.
Well, yeah. I suppose as you're looking down, it's rather two-dimensional, isn't it? Yeah. Well, it doesn't look like we're getting any questions through today. But
yeah,
I'm sure
get some three-dimensional information, but it's harder.
Yeah. Yeah, it is an interesting thing. I think it's another area of studying the climate that I think people probably don't think about. That's actually quite mathematical in the end. Yeah. Anyway, well, have you got any results from your second survey?
No, I haven't got. So I actually had an assistant in place to send me the results from the first one. I haven't got that for this one, so I can't tell you. Sorry.
Okay, well, you'll have to keep us posted with the results about that one. But in the meantime, since it doesn't appear there are any questions, I think that's a good place to stop for today. But thank you so much for presenting for us. It was a delight to hear all about the kind of things you're interested in, and yeah, to learn how to do some experiments of our own. So with that, I will say goodbye to the audience for this evening. And of course, don't forget that if you do want to watch this again, you can then watch the recording, which will go up on our website tomorrow. And so next week is our last Geo lecture before Christmas. And that will be with Mark Whitehead, who's joining us again to talk to us about about sustainability as a key geographical concept. So with that, I will say goodbye from Geo and goodbye from Sylvia. Thanks, everyone. So we're just saying goodbye.
Oh, I'm back.
That's all right. Just saying goodbye to the audience.
Bye.
Bye.